Okay, hello everyone. Today is the last talk for this year, and it's my great pleasure to announce Lisa Dunlap as today's speaker. Lisa is now currently a PhD student at UC Berkeley, and yeah, today going to talk about hyperparameterization on the cloud. And with that, let's take it from here.
All right. Yeah, sounds good. Yeah, thanks for inviting me. Yeah, my name's Lisa. I'm a PhD student at Berkeley. My work is sort of at the intersection of ML and systems. And so I'll be talking a bit about elastic hyperparameter tuning on the cloud. I'll talk a bit about the algorithmic side at first, and then a bit more of the systems components. So this will be a bit of a recap for most of you. But so at the core of all machine learning, as we probably all know, is this curve right here of accuracy over time. And so if you were to look at any ML paper today, you'd probably see a curve like this, or maybe, like an accuracy number, which the authors would want you to think is the accuracy, like the best possible accuracy you could have achieved. But in reality is the accuracy attained at whatever the conference deadline was or whatever the product deadline was. And if you were to just look at this, you would get a very optimistic view of how the ML development process actually works. So let's zoom out a bit to see what this process looks like a couple of weeks before like your conference or production deadline. So each of these lines on the graph here are going to represent a different trial or a different hyperparameter configuration you're running. So sort of in the beginning, you're going to run like a couple of different hyperparameters or a couple of different iterations of your method. Maybe in the middle, you'll run a few more. And then at some point, you'll realize like, oh crap, my deadline's in a few days or a few weeks, and you'll run a ton of these hyperparameters or trials all at once. And this is usually what people consider to be hyperparameter tuning. It's one of the most, if not the most, compute intensive part of the model development process. As someone who currently does a lot of computer vision research, I would say the majority of my experiments are hyperparameter tuning. And since the space of possible hyperparameters is incredibly large, it takes a lot of time and compute to even train one model to convergence. So it doesn't really make sense to train all of these possible hyperparameters fully. So oftentimes people will do this thing called early stopping, which is you'll sort of train a lot of hyperparameters for a couple of epochs and then sort of kill the ones that aren't doing very well, and then just continue training. And so what you want is this like red line here. So you want the best possible hyperparameter configuration, and that can have a pretty drastic effect on accuracy. And so this sort of deadline focused hyperparameter tuning is what we're sort of interested in. So I guess if you were to phrase it formally, how can we sufficiently explore the space of possible hyperparameter configurations to find a good trial so that we can train it for long enough to return a highly accurate model given some sort of like deadline and resource constraints? So on sort of both the algorithmic and the system side, this essentially boils down to a question of how do you balance exploration with exploitation? So this is like a sort of depiction of what this looks like. If you wanted to explore a lot of possible trials, like your possible search space was really large, the intuitive thing to do would be to run each of these on, say, a different machine, and just run them all in parallel. But the issue is this can be pretty slow. So you could also try this more like exploitation-based method where you put multiple machines on one trial or just like to train one model. That's going to increase your throughput. So you're going to train for more epochs within some time period. But where the sort of interesting thing comes in here is the fact that models don't scale linearly. So once you scale to a certain number of GPUs, depending on your model and your training setup, you're going to see diminishing gains in your throughput. So if you were to look at it from like a cloud perspective where like time and resources are money, you're getting a less cost-effective way of training these models because you're getting less throughput with the more resources you use. And so this idea of sublinear scaling is what makes this current work in hyperparameter tuning very interesting when you move to the cloud environment. So sort of up until this point, well, this point meaning about 2 years ago, because since then there has been more developments, but up until about 2 years ago, hyperparameter tuning algorithms have assumed some fixed cluster. So the user has a fixed number of resources, and in the cloud environment, you don't have this constraint, right? You can provision and deprovision machines at will, and so your resources are slightly different. For a fixed cluster, your resources or like your budget is usually the number of machines you have. And in the cloud, your resources are some monetary budget. Now you can translate both of these settings into sort of the same problem of how can we allocate machine time or GPU minutes to trials throughout our experiment in order to get a well-trained model by our deadline. But the key difference is how you're constrained to solving this problem. So in a fixed cluster setting, you sort of have to allocate a trial on each of these machines throughout training, right? You have to allocate your GPU minutes uniformly. Whereas in the cloud, you don't have these restrictions. And in fact, especially for cases where you want to explore, say, like hundreds of different hyperparameter configurations all at once, the cloud is seemingly a great option, assuming that it's easy to spin up several hundred GPUs at once, which is maybe a bit more questionable, but it's more likely you're going to be able to spin up like 100 GPUs to try out 100 configurations than to find a fixed cluster with 100 GPUs in it. And so these elastic resources allow us to come up with an allocation that doesn't suffer from these wasted GPU minutes due to sublinear scaling, which can lead to a model with higher accuracy than fixed cluster methods by a deadline. So sort of the like definitive problem setup here is I want to give you like, I have a hyperparameter tuning job. Here's my search space. I have 24 hours and I have $500. And I want you to come up with an allocation plan that I can run to minimize or to maximize my accuracy of my final model. Any questions so far? Okay.
Yeah, maybe sorry, maybe one question. So do you make any assumptions on availability at this point? So you might have not access to all of the machines at the same time. Or...
Yeah, so for this particular paper, we don't make assumptions on availability. We assume that if you want to provision a certain number of resources of a certain type, you will be able to do that. That doesn't always turn out to be the case. So that is an interesting thing to explore in future work. But for this, we make the assumption that you will always have the ability to get these resources.
Thanks. Yeah, makes sense.
All right. Yeah. So, all right. So in order to better understand sort of the intuition of our method, I'm going to go through a current state-of-the-art hyperparameter tuning method that I may or may not have also helped develop. So really just plugging all of my own work and show how we can better adapt it to the sort of elastic cloud environment. So here, this method is called Hypersked. At a very high level, it performs this idea of sequential elimination, which is running a lot of trials at once for a certain number of epochs and then killing off the worst performing ones and continuing to train the better performing ones. And then Hypersked at the end of an experiment will just pick like the best performing trial and allocate like all the machines to that trial in order to get that like last bit of accuracy. And so the trials that have good accuracy will be further trained and the others will be killed in order for new trials to be placed on the machine. So this is sort of an asynchronous method. And then this sequential elimination continues until all points are allocated, or all machines are allocated to the best performing trial. So this is in a fixed cluster environment. So if we were to move this to the elastic environment, we could do two things. First, we wouldn't need to run things asynchronously because theoretically we can spin up as many machines as we need. Now let's suppose our model only scales to say 3 GPUs. So like by scaling to 4 GPUs, you're essentially wasting that last GPU's time. And so on the cloud, wasted GPUs means wasted money. So what if instead we had the foresight of knowing that we don't scale to 4 GPUs and we're able to move that resource time to the beginning of the experiment to use it to test out, say, a new configuration. So if that were the case, there's a chance that this new orange trial would end up having the highest accuracy, and thus we'd get a better model at the end. So the idea is that the cloud environment should be exploring many trials at the beginning and deprovisioning machines as trials are eliminated, only keeping the ones that, only keeping the machines that would significantly increase the remaining trials throughput. And we sort of think that this is the direction that most hyperparameter tuning methods should be going. So in general, we think that this sort of triangle shape is more conducive to the cloud environment than this traditional rectangular shaped allocation of on-prem methods. So to sort of delve into the specifics of our method, I'll talk a bit more about the sort of related work or intuitions that we're building off of along with this cloud stuff. So essentially our method has what we call different brackets that play off of this idea of exploration and exploitation. And so it's based on the idea that models with different hyperparameters converge at different rates to different accuracies. So if you have models that converge really quickly, then you would want to have this more like exploration strategy because you don't need to train them for very long in order to know if they're bad. And if you had something with, say, slow convergence, you would want this sort of exploitation strategy because you need to run them for a much longer period of time in order to figure out which one is the best. The issue here is that you don't actually know which trials are quick or slow to converge. And so what we do, which is somewhat similar to other methods, is we employ this sort of bracket-like strategy. So this is sort of hedging our bets, where you have these exploration brackets, which usually contain more trials that are run on fewer machines, and these exploitation brackets, which contain less trials and are given more machines per trial. So here you can sort of see the stages through time on the x-axis. So each bracket conducts this idea of sequential elimination. And if a trial in an exploration bracket obtains a higher accuracy than a trial in the exploitation bracket at the point of evaluation, they'll be swapped. So like in this case, the yellow trial will be swapped with the green trial, because it obtained like a higher accuracy. And so this is beneficial in two ways. First, giving the yellow trial more resources will give us more information as to whether it will outperform like the blue trial, if you were to, these correspond with the graph. And it would also train it for longer so that if it does turn out to be the best, it will have hopefully converged and have high accuracy by the deadline. So yeah, and one other important thing to note is that there will never be a bracket that assigns more machines to a trial than is useful. So this is sort of a user provided input of how many machines your trial can scale to. That's like a function of your throughput scaling with number of machines. And so essentially we bake in the fact that you will never have these like problems with sublinear scaling. And then I'm not a huge fan of tables, but if you want to know, these are compared to a lot of other different elastic and like fixed resource hyperparameter tuning methods. And we see that we obtain high accuracy given the same cost and time budget. Any questions on Seer? Okay.
Sorry,
Yeah.
I have a question. It seems like you rely a lot on this assumption that there is a deadline. Is it something that you use as a time horizon for your bandit problem? So is this a problem that allows you to allocate resources depending at which stage you are in your bandit problem? So how close you get to the final let's say capital T time?
Yeah, so I'm not as good on the theory of bandits here, but basically when you add in this time horizon, you can't really make any of the theoretical guarantees that you have with this infinite time horizon. I don't know if that actually answered the question.
Yeah, I mean, I was just wondering if it's an assumption that you need in order to schedule different configuration with different resources, or is something that is just part of how you see the problem and it doesn't really have a role in the algorithm?
Oh, yeah. So I guess this method in particular does particularly require a deadline. So there are a lot of hyperparameter tuning methods, mostly the asynchronous ones, that don't assume any time horizon. And so that was sort of I feel like that is the majority of hyperparameter tuning algorithms don't assume a deadline. We're specifically interested in this idea of a deadline because it seems like a much, I don't know what you would call it, a much cleaner solution. Like if I'm running hyperparameter tuning experiments, I don't really want to run it in two phases where I run one to find the best job and then run another to like train that best job again. But yeah, so these methods do require a explicit deadline.
Okay, thank you.
Yeah.
Yeah, similar follow-up question. Do you also, does a method assume that you have the brackets given? Or because in practice, quite often, you train a transformer, you train it for longer, it's going to get better. And and most methods out there just is that are based, for example, on successive halving, etc. Okay, this is a max budget and you just can't do more than that. Sometimes that is very limiting. Also, that's something that we get from users very often as a question. How do I set these brackets? Do you have any thoughts on that?
Yeah, so I guess are you talking about like in terms of brackets, like the length of time you're training? or
Length time, you can also then scale it up, right?
Yeah.
Just add a few layers. It's going to get better if you train for longer, but there's this clear interaction effect.
Yeah. So, let me try to find a good way of. So it does require user knowledge of how much you should be training in order to like train to convergence. So if you were to provide like a very short deadline or like a very low cost, because these brackets are determined automatically, so the number of epochs that you're training your final model for is not guaranteed like beforehand. So you do kind of have to play around with like what your time and resource constraints are in order to make sure that in your final bracket, like your last few trials will be training for long enough. There is part of it that is sort of baked in of like with successive halving, if your models are sort of converging slower, you're automatically going to train those for longer. But there's one other thing. But yeah, so you do have to know essentially how long you need to train for. And then also we sort of make the assumption that different hyperparameters don't affect the throughput of a model that much, which doesn't necessarily scale. Like if you're doing something like neural architecture search, those guarantees don't hold. I do know that there have been some works that look into using neural architecture search with these methods, and they seem to still work. But yeah, there is still a bit of like, you still need this user knowledge of how long to train things for.
All right, thanks.
Hey,
Right.
I have a question also to the previous slide, also regarding the brackets. So I think to my understanding, you also need the user knowledge of like how you want to design the brackets in terms of how many GPUs you have, and then also of like how good potentially models parallelize across multiple GPUs, right? Or is this just assumed to work well?
Yeah, so you don't have to make any assumptions on the number of GPUs you have, or like the number of like configurations you want to use. The only thing you need to provide here, along with a cost and resource constraint, is a cost and a time constraint, is this like scaling curve of what you would suspect the expected throughput scaling to be with number of machines. But the method itself determines how many GPUs you need, how many like trials to put in each bracket, how many GPUs to put in each bracket, things like that.
Oh, all right, thanks.
And super quick follow-up here on the scaling. So on the left, you have this graph, and yes, you never have quite linear scaling, but your method assumes user input that says you will have linear scaling up to n GPUs, and up to there you can do whatever you want. Don't go above that. Is that correct first? And if that's correct, could you also instead basically put in a graph like on the left where you say, well, you're gonna get 5.7-fold speedups if you use 8 GPUs, and do with that whatever you think is good.
Yeah, so in this one, you actually can put in this like graph of like a function of number of GPUs. I will say this doesn't work as well as the paper I'm about to present next utilizes this graph a bit more. But you can put in this like function of throughput through time, but it does often just come out to like, the method will just say, oh, okay, so I just shouldn't provision past X number of GPUs.
Cool, thanks.
All right, any other questions? Okay. Yeah, so I guess that leads into the second part of my talk, which is Seer was all about finding a good hyperparameter job to run. But then there's also the question of like, what if I already have a hyperparameter tuning experiment in mind where I know like how, like I say I want to do this successive halving, I know how many trials I want to try out, I know like how many epochs I want to train each like stage for, each trial in each stage for. And I just want like a system that will minimize my minimize my budget on the cloud while still finishing within some set deadline. And so that leads to Rubberband, which is from Eurosys, I believe, 2021. And so it's based around the same idea as Seer, which is like, in the end, you want this allocation plan of like how many trials or how many GPUs to give to each trial. But this just operates under the larger constraint of the users providing how many epochs to train each model for and how many total models to train for each stage. And so all that it is trying to do is figure out what the correct allocation plan is, how to actually allocate the machines, like how to co-locate like the jobs on machines. So this is an actual sort of system we built as opposed to this algorithmic work of Seer. And so we kind of boil it down into 3 challenges. So the first is, how do you like accurately model the execution of a job on the cloud as a function of this like resource allocation plan, which is what defines the number of parallel compute resources to allocate to each stage of the job. So this is like, how do you find this model scaling? How do you find how long it takes to train a model for one epoch? And then the second is now you have this large search space of possible like allocation plans. And how do you sort of navigate through this large search space to find a low cost solution that completes within the given deadline? And then the third is, how do you efficiently schedule and place these workers over these elastically provisioned clusters so that we can optimize for worker co-location and maximize cluster utilization. Before I continue, does the concept of an allocation plan make sense to people? I don't know if I explained that well enough. Okay, I'm gonna assume it did.
There were some thumbs up here, so yeah, I think people.
Okay, perfect. All right, so to address these challenges, we designed Rubberband, which is a fantastic name that I sadly didn't come up with, but it's a framework for cost-efficient, elastic execution of hyperparameter tuning jobs. So Rubberband introduces this DAG-based execution model that captures the various latencies and costs associated with executing a job on the cloud over a given resource allocation plan. And so this model is parameterized by profiling your deep learning model's training latency and resource provisioning overheads prior to your execution. And then you can Rubberband searches for a feasible, cost-efficient resource allocation plan, utilizing the execution model to predict the end-to-end job completion time and cost of the input job for each candidate plan. And then during execution, Rubberband elastically scales the underlying cluster according to the plan and like dynamically allocates provision resources fairly among the trials and manages the placement of individual workers. So that was kind of a lot. So to like boil it down, we develop a cost and latency model that synthesizes this profiling information about the input job and cloud resources to evaluate the benefit of running these different allocation configurations of your hyperparameter experiment. And then based on this profiling, you can use this DAG-based execution model to get the estimated job completion time of each potential allocation plan you come up with. And then this execution model will ultimately return the resource allocation plan that minimizes your cost while still finishing within some deadline. And then we build this full stack system for hyperparameter tuning, which generates and executes this optimal placement plan to maximize worker co-location and cluster utilization. So here's a rough depiction of what the system looks like. We build Rubberband on top of Ray, a distributed computing platform that hopefully some people have heard of. So the pink arrows here represent invocations, and the gray arrows here represent object dependencies. And so we have these sort of three components that we addressed in the previous slide. The profiler and simulator are sort of together, and they work with the planner to come up with the optimal allocation schedule. And then that goes into the scheduler, and like the placement controller and the cluster manager help actually schedule these jobs on the cloud. All right, so now I can go into sort of each of these three components. So in order to model the job completion time and cost, we need two things: data pertaining to the performance and cost of your job, and a simulator to utilize that data to determine the overall performance and cost. And so we also need to take into account the potential fluctuation of training latency to ensure that we don't end up with stragglers, because this is a like a synchronous stage-based program or allocation plan. And so to obtain the data pertaining to the performance and cost, Rubberband just runs a profiling step for a configurable period of time prior to the execution to collect data associated with model training and resource management. And so this process just involves like iteratively scaling up and down the resource allocations to each model. So what's the throughput of my model at 1 GPU, at 2 GPUs, at 4? So you can get this like nice scaling curve that we showed before. And then once that data is collected, you can use that to simulate the latency and cost of these like candidate resource allocation plans. And then for each, oh, I didn't show this DAG model. And then for each allocation plan, Rubberband like has a simulator that synthesizes a DAG here that incorporates the cost and latency of initializing the instance, scaling up or down, training the models with a specific number of resources, taking into account this idea of the model scaling function, and evaluating the model accuracy at the end of each stage of your experiment. And so on the right here, like in this diagram, we've shown an example of how this looks when we give it a successive halving experiment with 3 stages. So we see the 3 stages and that they all have a sink at the end of them. And so to account for potential stragglers, we sample the latencies of each node to get a, or we sample the latencies of each node from like a distribution that we come up with by profiling the like throughput data. And then once this DAG is generated, you can have, our planner predicts the job completion time of candidate allocation plans by computing the critical path on this DAG. And so cost can also be calculated in a pretty similar manner with differing methods for things like per function billing model and your per instance billing model. So this should be able to work for multiple different cloud providers, different types of instances. And it's all sort of wrapped up in this nice, I don't know what you would call it, this profiler essentially makes it so that you don't need to be adding in all of this extra information about like your model throughput that you may not initially know beforehand.
Sorry, quick question here. So I see that it works for different types of instances, but for within a job, you assume it's always the same instance, right? You don't like have a heterogeneous set of instances here.
Yeah, so we tried playing around with the idea of like multiple different instance types, but that ended up being too many variables. So we do assume that it's the same instance type.
Yeah, okay, that's fair.
And also a quick question, sorry, while we had questions. You mentioned it's synchronous. I'm sort of surprised by that because you have all of this really cool stuff and then you make it synchronous on the cloud. Really? Is that needed, or is it actually not holding you back in any way? I would have thought it holds you back. Yeah,
so I mean, with the way that we proposed Rubberband, you actually could give it an asynchronous like experiment. Like there's nothing that makes it have to be synchronous, but our sort of argument is that it doesn't, if we are assuming that you have some sort of finite time horizon on the cloud, it doesn't make much sense to have, and you can, you know, have a counter argument, but it doesn't make that much sense to have these like asynchronous hyperparameter tuning jobs, because if you assume that you can provision the right number of resources in the beginning, you're going to save time by like running all of the potential configurations you're going to run all at the beginning, which is why we kind of talk about this synchronous model.
Right. I guess if you assume that all the models take similar amount of time. So again, your architecture search might be tough, or?
Yeah. So yeah, this again is like makes a similar assumption of not assuming that your different models take in different like, or different configurations have different latencies. I'm trying to think of, is there a reason why in neural architecture search an asynchronous approach would be preferred?
Well, it doesn't have to be NAS, but also HPO if you want to use more layers or more widths, or like it's just architectural hyperparameters that just give you different complexities of training, and you need to let it train for a while in order to see anything.
Yeah, that's true. And yeah, and I guess the straggler issue would probably be a lot more with neural architecture search.
Okay, cool. Just trying to understand. Thanks.
Yeah, no, yeah, well, I love the questions. All right, so now it's stage 2, which is finding this low cost allocation plan. And so now that we've figured out how to best model the performance and cost of a given allocation, we need to find the actual allocation plan that minimizes this cost before a given deadline. So this is where our like planner comes in. So it's responsible for generating feasible resource allocation plans that minimize the predicted execution cost. And so to do so, the planner warm-up starts its optimizer with some feasible solution, and then we improve the plan in like a iterative greedy fashion by generating a set of new candidates from the current best, predicting each of their job completion times and cost using our sort of stage 1 simulator, selecting the best candidate, and then iterating until the best candidate generated is no longer predicted to improve cost or violates the time constraint. Oh, sorry. A telemarketer is calling me. And so in the end, we come up with this optimal allocation plan that maximizes this cost marginal benefit, which is the reduction in cost of one plan from another, normalized by the increase in runtime. And so, yeah, we want a plan that reduces cost without significantly increasing job completion time. Okay. And so now that we have this allocation plan, we need a way to schedule and optimize this like worker co-location to maximize our cluster utilization. So Rubberband's executor comprises of a control loop that makes scheduling decisions based on the experiment specification, resource allocation plan, and the current state of the running trials. So if the current cluster needs to change the resources needed, if the current cluster needs to change or the resources need to be reallocated, which would happen like at the end of a stage here, the scheduler would request the cluster manager to provision new nodes or to deprovision existing ones. And then to reallocate workers, the placement controller would convert the resource quantity allocated to each trial into some physical resource assignments for each worker. And then parallel workers of a trial should be co-located on a single machine or packed into a minimal set of nodes in order to reduce communication. And so you won't have any unnecessary network overheads. And we do sort of operate, depending on the instance type you're recommending, we do sort of operate in these units of like, if you have a 4 GPU box, we operate in units of 4. So you'll never have a machine where you only have like 3 of 4 GPUs being used. So here's some end-to-end results. And so comparing to some fixed cluster methods, this just shows that our simulation quality is pretty good. So this graph shows that the simulated predictions of the job completion time and cost when running like a 20-minute experiment is like pretty similar to the real job completion time, and the cost when running on, what did we run on? P3.8 large instances. And so we've shown that the simulation is pretty accurate. And then what sort of the more important part is are we able to do these hyperparameter tuning experiments where we're training each of these to like state-of-the-art accuracy, and showing that compared to static methods, Rubberband is able to achieve the same accuracy because they're running the same plans, while seeing like a very large reduction in cost. And then this is across different deadlines, and as the deadlines increase, the cost savings of Rubberband decrease because as the time horizon increases, it makes less sense to put more resources on a trial. And so the optimal allocation plan usually becomes run each model on 1 GPU. So yeah, in conclusion, Rubberband utilizes this performance, instrumentation, and cloud pricing to model job completion time and cost prior to runtime. And they can use that to generate a cost-efficient, elastic resource allocation plan, which is dictated by the sort of same motivation as Seer, which is this like triangular allocation plan is always going to be preferred to this rectangular allocation plan that you see in fixed resources. And then Rubberband's able to efficiently execute this plan and realize a cost reduction of up to 2x in comparison to static allocation baselines. Yeah, that's about it. Happy to answer any questions.